In this video, we will demonstrate how to use Visual Python to describe and simulate the motion with constant velocity. So we have 3 steps to perform the simulation. First is to set the initial condition for the particle. Second is to visualize the motion using a representative object, namely a sphere, and then perform the simulation using a while loop. So in the simulation, we will get the equation for linear motion and then update the time for a given interval. So for example, we want to simulate the motion for 5 seconds. So we set the time interval for the simulation using the while loop. So for the initialization, what we will input is the initial position and the initial velocity of the particle. So we can spell out the variable for the position. So let's say the position is along the x-axis. So we represent this as a vector 1, 0, 0. And the initial velocity should also be represented as a vector. So although this motion is in 1D, it's better to use vector notation because this will generalize the input values for the simulation. So if you want to simulate in 3D, then you can put values for X, Y, and Z components simultaneously. And we initialize the time at 0. So time is in seconds. The velocity is in meters per second. And the position is in meters. Another thing that we want to initialize is the step size. So this is the increment for time. So let's say we fix this at 0.01. Time step or step size dt. Now, if you want to create the object, let's say ball 1, we represent this using the sphere function. So we put the attributes of the particle inside the sphere function. First is the position. So since we already initialized the position, you can call the variable for the initial position in line 5. So we just write initial underscore position. And then we also have the velocity given as initial underscore velocity in line 6. Although you can write initial velocity in this form, and also for the initial position in the form vector 1, 0, 0, I'm just showing how we can use variables as representation for the attributes. You can also have color attribute. Let's say yellow. And of course, the dimension. We fix this at 0.1. So if you run this simple code, we will see that the particle is located at a distance 1 meter from the origin. So the canvas, the black canvas is centered at the origin. So if you make the position vector -1, 0, 0, then you place the particle in or to the left 1 meter to the left of the origin. Next is to simulate the motion for a given interval. So for example, we want to simulate the motion in the time interval equal to 5 seconds. So that means that we update the position by adding the initial position and the product of the initial velocity and time. So you start at t equals 0, and then at time t equals 0.01, you again add, and so on. So here, what we only need is the time interval value, which is 5 seconds, to be multiplied here so that we can solve for the total distance traveled by the particle. But what we want is to simulate the motion frame by frame, and each frame has a duration of 0.01 seconds. So that's the step size. So inside this procedure, we will create a while loop. So in the while loop, you just define the condition when the simulation will run. So we will limit this in the interval 5 seconds. So 5 seconds. So we use less than or equal to 5 seconds. So after this is being reached, the simulation will stop. So if it is less than 5 seconds, so it means that before reaching the value 5, the simulation will be terminated. So the first value that you need to include is the frame rate, or the number of computations per second. So here we limit it to 100. It means that every second there will be 100 computations. So take note that you start with 0.01, and then you your upper limit is 5. So that means you have to include all the increments from 0.01 to 5. So that's equal to 500 iterations. Next is to include the equation. So the position now will be updated. So take note, for ball 1, the position is given here. So you just call that attribute ball1.pos is equal to the initial position plus velocity. So that's initial velocity times time. So the first value is t equals 0. So that means the ball's position will be equal to the initial position. After that, you iterate the time value. So 0 plus the increment dt. So it becomes 0.01. So for the next iteration, time will now be 0.01 multiplied to the initial velocity times the initial plus the initial position. until it reaches 5 seconds. So running this code, you can see that the object moves from left to right. So you can also adjust the interval. If you make it 3, then after 3 seconds, the ball stops. So to visualize the motion, what you can do is to include a trace, use the make trail attribute equals true. So this will leave line trace behind. So there's another option that is to change the trail type to dots or points. So you can see that you have adjacent points left behind. So to lessen the number of adjacent points, you specify the interval. So if you fix that to 10 points per second, so you will have separate point traces. You can also change the color if you want. So trail color is equal to, let's say, green. Just to differentiate the trace with the particle's color. So that's how we simulate the motion of a particle using the theoretical equation. So we can call this as theoretical simulation or theoretical version of the simulation. The other way of simulating is to define the update equation starting from the velocity equation. So we know that the velocity of the particle is defined as the change in position divided by the change in time. In vector form, this is delta r divided by delta t. This is the rate of change of position with time. So if you want to write the change in position, you just multiply the velocity. So this is the velocity at time t. You multiply that by delta t. So for the update equation for the velocity, so you know that delta r is equal to r minus r naught. But in numerical simulation, we define r as the new position to be updated, and r naught is the previous position, which will be added to the current velocity multiplied to the time step. So you can write r as r new. So this is the position to be updated is equal to r old. So that's the old value or the previous value of the position plus velocity times delta t. To implement that in Visual Python, we add another line for the numerical update equation. So what we will do is to represent the motion using another object. So we define another particle. So let's label this ball 2. And then we just change the color. So we make this red. And the trail color, we make this, say, purple. So without the numerical update equation, you can see that the particle will just stay at the initial position, -1, 0, 0. Okay, so let's save this first. Medyo matagal yung update niya. And then let's run again. So the motion being simulated is based on the theoretical equation. X is equal to x naught plus v naught t. So for the numerical update equation, we will use ball2 dot pos. So we will update the position of the ball. So instead of using the initial position, we will use the previous position, ball dot pos plus the initial velocity. But instead of using the initial velocity given in line 6, we can start for the velocity to be updated, we should use the velocity attribute for ball 2. So we call that attribute ball2 that v times dt. So instead of using time, we use dt. So for each increment or interval, we will get a new position and a new velocity. So let's say we fixed first this to 2 seconds so that we can have a larger perspective. For the interval, so let's say it starts at position given at -1. So to update the new position, R new, you need the value at this point, R old. So for the next iteration, the second point becomes the old value of the position, and then the adjacent position will become the new position. So that is how position is being updated. So for each time step, you get a new value for the position and for the velocity. That's why we use dt instead of t. So to differentiate the two, you can place the second one just above. So 0 and then 0.5, 0. Para magkatabi sila. Yan. So you can see that they are almost identical. What if we change the time interval to 0.1? So you can see that for 0.1, nag-advance yung numerical simulation. Let's adjust this to 0.2. So there's a shift. How about 0.05? So you can see the shift in the data points for each time step. But as we decrease the step size, 0.02, you can see that the two traces become more identical. So if we remove this offset para pagtabihin natin sila, you can see that the red ball is advancing as compared to the yellow ball as given by the traces. But if you decrease this or you make this smaller, 0.01, so again, if you decrease the step size, you increase the number of computations. So what you can do is to change the frame rate. You increase this by 1. This is just 1 over the step size. So you, instead of 1,000, you can also write this as 1 divided by dt. It's the same. So the two particles have identical traces as you decrease the time step or the step size. So the numerical simulation becomes identical with the theoretical simulation with smaller time step. So the numerical simulation uses discrete values, while the theoretical simulation uses the continuous function x equals x naught plus v naught t. So upon simulating the motion, we can also visualize the simulation using graphs. So above this, we can create graphs for simulation. So in creating graphs, what we need is a template. So let's say we call that graph 1. So we use the graph function for the template. And then for the plotting, we can use g-dots or g-curve. So we just name the graph using any variable. So let's say we want to plot position versus time is equal to g-curve. So below the update equation, you can call for the function. So for plotting, we use pos versus time dot plot, and then indicate the x and y components. So the x component is time, and the vertical component, meaning the y-axis, will be the position in x. So that's ball1 dot pos dot x. So you need to specify the component because we can only plot one component at a time. So here is the plot. So take note that we want to plot the numerical and the theoretical simulation. So we can also use g-dots if you want. you can get the same result. You can adjust the step size, 0.01. And then include the plot for the numerical, or for the, yes, numerical part. So the first plot is for the numerical. So position underscore numerical. We have G dots. And then we put label. So this will be for the, no, ball one is theoretical. This is the theoretical part. So we label this theoretical, and then we also label this as underscore theoretical. So we change this to numerical, position numerical, and then we label this as numerical. So to compare the two, we change the theoretical to curve, and then we include color just to differentiate the two plots. So for the numerical, we use scatter plot, and then we change the color to red. So after line 24, we call this function numerical position versus time dot plot, and then identify the x and y coordinate. So the x coordinate is time, y coordinate is ball2 dot pos dot x. So take note that x and y, or x, y and z components are both 0. And then for the plotting, we can only plot one component at a time. Okay, let's run the simulation. So you can see that the numerical and the theoretical values coincide with each other. Okay, let's change the other one to G dots. Let's make this G dots. And then change the interval to 1. We can also add labels. So the x component, or the x coordinate, is time in seconds. Y title is position. In meters. So here we have the position versus time plot for a ball moving at constant velocity. So for example, you want to solve for the slope of the line. You can have a third-party plotting app. So just include it in the graph attribute. So if you want to make the graph editable, you just include fast equals true. So if you run this, you can make the plot interactive. Oh, wait. I don't know if we should put it here. Okay, let's run again. No, it's not working. Okay, run. Oh no, it should be false. Fast equals false. Okay. So by putting the attribute fast in the graph, you can take a snapshot of the plot. You can also edit the plot. You can also trace the region you want to study. So you can have zoom, you can zoom in or zoom out the values. You can compare the two values. You can zoom in. Okay. You can auto scale. So if you want to see the coordinates, for each point, you can see the interval given by these broken lines. So by clicking this chart, you will be directed to the online data analysis app. So if you want to analyze, for example, the plot, you click Analyze and then use curve fitting. So we know that the slope of the line is the velocity. So we indicated that in the theoretical value. So let's check if we get the correct value for the numerical plot. Or first for the theoretical. So use basic. We use linear fit. We just run the app. So the slope is 1, which is just the velocity. Initial velocity is 1. So if you want to look at the slope of the other data, numerical, and then use linear, and then run again. So we get m to be equal to 1. Okay. So the only difference is that now we have a discrepancy in the intercept. So take note, the intercept is the initial position. So instead of getting -1, because that's the initial x position given in line 9, we get -0.9899. which is approximately equal to the initial position also. So there's a slight discrepancy because the step size is fixed at 0.01. So there's a discrepancy of 100th. So the Plotly app is separate from the Trinket, but we can link the data analysis with your simulation when you specify the feature in the graph. So I hope you learned something in this brief demonstration. Feel free to use the Trinket code. You can also modify it for your own simulations.